Every rigorous experimental design must account for nuisance factors. These are variables that likely influence our response variable but hold no inherent interest to us as researchers. The critical challenge is that while we don't care about these factors themselves, they introduce unwanted variability into our measurements, and this variability can obscure the effects we're actually trying to detect. Consider some concrete examples. Raw material batches often differ in composition. Different operators may apply procedures with varying precision. Test equipment can drift or malfunction. Time itself introduces variation. Measurements taken across different shifts or days may be affected by environmental conditions or operator fatigue. Even the experimental units themselves, whether they're manufactured items or biological specimens, naturally vary from one to another. Now, what happens if we ignore these sources of variation? The answer is straightforward. Our experimental error increases. When nuisance factors go uncontrolled, their effects get absorbed into the error term, inflating our estimates of variability. This makes it harder to detect true treatment effects and reduces the power of our statistical tests. We might fail to find significant differences that actually exist, or conversely, we might attribute random noise to our treatments. The solution lies in systematically managing these nuisance factors through two distinct strategies, which we'll examine in detail on the next slide. Having established what nuisance factors are and why they matter, we now need to classify them systematically. The distinction hinges on two critical dimensions: whether we can control the factor and whether we know it exists beforehand. We recognize two primary categories. Blocking factors are known sources of variation that we can actively control or manipulate in our experimental design. Conversely, covariates are known sources of variation that we cannot control. We can only observe and measure them as they occur naturally. Consider a practical example. If we're running an experiment across multiple days, and we suspect day-to-day variation affects our results, we might treat day as a blocking factor by deliberately balancing our experimental runs across different days. Alternatively, if we're measuring humidity in a laboratory and suspect it influences our response, but we cannot regulate humidity, then humidity becomes a covariate that we must record and account for statistically. Both types can be either qualitative or quantitative in nature. A blocking factor might be categorical, like different operators, or numerical, like temperature settings we control. Similarly, a covariate might be a categorical variable like batch identification or a continuous measurement like ambient pressure. This classification framework will guide our choice of analytical strategy, which we'll examine in detail on the next slide. Now that we've established the two categories of nuisance factors, let's examine how we address them systematically. The framework presented here organizes our strategies along two dimensions: whether the factor is known or unknown to us, and whether we can control it in our experimental design. When we know a nuisance factor and can control it, we employ blocking. This is our most powerful approach because we actively manage the source of variation. Conversely, when a factor is unknown, randomization becomes our defense mechanism, distributing its effects unpredictably across treatment groups. The more challenging scenarios occur when we have incomplete information. If we know a nuisance factor exists but cannot control it, perhaps due to practical or ethical constraints, we must observe it and account for it in our analysis. This is where analysis of covariance becomes essential. Additionally, when factors are entirely unknown, randomization again serves as our safeguard. This table essentially maps our methodological toolkit. Each cell represents a different challenge and its corresponding solution. Understanding which cell your experimental situation falls into determines your analytical approach moving forward. Having established how to handle nuisance factors through blocking and randomization, we now turn to a specific analytical technique for managing uncontrollable factors that we can measure. When we identify such a factor as a covariate, we employ analysis of covariance, or ANCOVA. ANCOVA is particularly valuable when we have an uncontrollable factor that influences our response variable but is not itself affected by our treatment assignments. This distinction is crucial. The covariate must be independent of the treatment, otherwise our estimates become biased. The method works best with quantitative covariates, which allows us to leverage regression techniques to model their relationship with our response. By incorporating this quantitative information into our analysis, we can reduce unexplained variation and increase the precision of our treatment comparisons. The fundamental advantage of ANCOVA is that it allows us to adjust our treatment effect estimates to account for differences in the covariate across experimental units. Rather than ignoring these differences or hoping randomization balanced them, we explicitly model and adjust for them statistically. This leads to more powerful hypothesis tests and more accurate inferences about treatment effects. Having established what ANCOVA is and when we apply it, let's examine the underlying model structure. The fundamental purpose of ANCOVA is to isolate and compare treatment effects while statistically controlling for one or more quantitative covariates. We accomplish this by assuming a linear relationship between our response variable and the covariate. This linearity assumption is critical because it allows us to visualize the analysis geometrically. When we plot the expected value of our response against the covariate, we should observe a set of parallel lines, one for each treatment group. The key insight here is that these lines are parallel, meaning the slope remains constant across treatments. This parallelism enables us to make fair comparisons of treatment effects at any given value of the covariate. In other words, we're adjusting for the covariate's influence while preserving the ability to compare how different treatments affect our response. The next slide will present the formal mathematical model that operationalizes this conceptual framework, allowing us to estimate these treatment effects precisely and conduct appropriate statistical inference. Building on our previous discussion of parallel regression lines, we now formalize the analytical framework. The analysis of covariance model provides the mathematical structure that enables us to compare treatment effects while simultaneously controlling for one or more continuous covariates. This model is particularly powerful because it allows us to adjust for baseline differences between groups before making treatment comparisons. By incorporating the covariate into our regression framework, we can isolate the treatment effect from confounding influences. The key insight is that when we fit this model, we obtain regression lines for each treatment group that are parallel to one another. This parallelism assumption is crucial. It means the treatment effect is constant across all values of the covariate. Consequently, we can make meaningful comparisons of treatment effects at any specified value of the covariate, whether at the mean or at other clinically relevant points. Notice that the model structure differs subtly from simple linear regression. The inclusion of treatment indicators alongside the covariate creates a more nuanced picture of how our response variable behaves. This distinction becomes particularly important when we interpret the parameters, as we'll see on the next slide when we examine how the overall mean is redefined in this context. Now we need to clarify an important distinction regarding the overall mean in our analysis of covariance framework. In the standard regression model we discussed previously, the overall mean represented the expected value of our response variable when all predictors equal 0. However, in the context of analysis of covariance with a categorical factor, the situation becomes more nuanced. The notation uses m with a prime or m prime to denote what we now call the overall mean. This distinction is crucial because m prime is no longer simply the intercept from our original model. Instead, it represents the adjusted overall mean, accounting for the presence of our covariate. Specifically, m prime is calculated as the grand mean of the response variable evaluated at the average value of the covariate across all groups. This adjustment becomes necessary because we're simultaneously modeling both the effect of our categorical factor and the linear relationship with our continuous covariate. The adjusted overall mean thus provides a baseline that reflects the typical covariate value in our sample, allowing for more meaningful comparisons across treatment groups. This foundation is essential as we move toward considering whether the relationship between our covariate and response truly remains constant across all groups, which brings us to the question of equal slopes. We now turn our attention to a more flexible formulation of our regression model. The previous specification assumed that the relationship between our predictor and response variables remained constant across all groups. That is, the slopes were identical. However, this assumption may be overly restrictive in many practical applications. To address this limitation, we generalize the model to allow for differential slopes across groups. This means each group can have its own regression coefficient, capturing potentially different rates of change in the response variable relative to the predictor. This extension provides considerably more flexibility in modeling heterogeneous relationships within our data. The mathematical formulation of this full model, which permits unequal slopes, will be our focus moving forward. Once we've specified this more general framework, we can proceed to derive the least squares estimates that minimize the sum of squared residuals under this expanded model structure. These estimates will give us the optimal parameter values for each group's intercept and slope, allowing us to characterize the distinct relationships present in our data. Having established the framework of equal slopes in our previous discussion, we now move to the full model specification. This generalized model allows us to estimate the regression parameters without the restrictive assumption of parallel lines across groups. The least squares estimates for this full model are derived by minimizing the sum of squared residuals across all observations and groups simultaneously. These estimates provide us with the optimal values for the intercepts and slopes that best fit our data under this more flexible framework. The key distinction emerges when we consider the degrees of freedom. For the full model, we have fewer degrees of freedom available for estimating the error variance compared to the traditional ANOVA case. This reduction occurs because we are now estimating additional parameters, specifically, separate slope coefficients for each group rather than assuming a common slope across all groups. This increased model complexity consumes additional degrees of freedom, leaving us with one fewer degree of freedom for error estimation. Understanding this trade-off is essential. We gain flexibility in our model specification, but at the cost of reduced degrees of freedom for estimating the residual variance. This relationship between model complexity and degrees of freedom is fundamental to statistical inference and model comparison. Having established our least squares estimates for the full model, we now turn to estimating the error variance, denoted as squared. This estimate is obtained by dividing the residual sum of squares by the degrees of freedom associated with the error term. You'll notice that we have one fewer degree of freedom available here compared to what we'd see in a standard ANOVA framework. This reduction occurs because we're now accounting for the covariate in our model. In ANOVA, degrees of freedom for error equal the total sample size minus the number of treatment groups. However, in ANCOVA, we must additionally subtract 1 degree of freedom to account for estimating the slope parameter of the linear relationship between our response variable and the covariate. This adjustment reflects the additional constraint imposed by fitting the regression line. The resulting estimate provides us with a measure of unexplained variability after accounting for both treatment effects and the covariate's influence. This refined estimate becomes crucial as we move forward to validate our modeling assumptions, particularly the critical assumption of linearity between the response and covariate within each treatment group. Having established how we estimate the error variance for the full ANCOVA model, we now turn to a critical diagnostic step, verifying that our model assumptions actually hold in practice. Beyond the standard assumptions we make about errors in any regression model, ANCOVA introduces one additional requirement. We must assume a linear relationship exists between the expected value of our response variable and the covariate across all treatment groups. To assess whether this linearity assumption is satisfied, we employ a graphical diagnostic approach. Specifically, we plot the residuals against the covariate, creating separate plots for each treatment group but displaying them on the same scale. This side-by-side comparison allows us to evaluate whether the residual patterns remain consistent across treatments. If any treatment group exhibits a nonlinear pattern in its residual plot, perhaps showing curvature or systematic deviation from a horizontal band, this signals a lack of fit. Such a finding would indicate that our linear model is inadequate and we would need to consider alternative specifications, such as including polynomial terms or other transformations of the covariate. This diagnostic check is essential before we proceed to hypothesis testing, as violations of the linearity assumption can compromise the validity of our subsequent inferences. Now we turn to the formal hypothesis testing framework for ANCOVA. The fundamental question we're addressing is whether the treatment effects are equal across all groups, or whether at least two treatment groups differ significantly from one another. Under the null hypothesis of equal treatment effects, our model simplifies considerably. The treatment parameters vanish, and we're left with what amounts to a simple linear regression model where the response variable depends only on the covariate with a constant intercept term. This reduced model serves as our baseline for comparison. The key insight here is that by imposing the null hypothesis, we eliminate the treatment structure entirely. Every observation, regardless of group membership, follows the same linear relationship with the covariate. This simplification allows us to estimate the regression parameters more efficiently under the assumption of no treatment differences. In the next section, we'll derive the least squares estimates specifically for this reduced model. These estimates will become crucial for constructing our test statistic, as we'll compare the fit of the reduced model against the full ANCOVA model to determine whether the data provide sufficient evidence to reject the null hypothesis of equal treatment effects. Having established our null hypothesis and the reduced model structure, we now turn to estimating the parameters under this constrained framework. When we assume all treatment effects are equal, the least squares estimation becomes straightforward. We're solving for the intercept and the common slope coefficient by minimizing the sum of squared residuals under this simplified model specification. These estimates follow directly from ordinary least squares regression principles, where we have a single predictor and a constant term. The key distinction here is that we're no longer estimating separate effects for each treatment group. Instead, we have one global slope that applies uniformly across all observations. Once we obtain these least squares estimates, we can compute the fitted values and residuals under the reduced model. These residuals then allow us to calculate the error sum of squares, which becomes our basis for estimating the error variance sigma squared. This variance estimate under the reduced model will be crucial for our subsequent model comparison, as it provides the denominator in our test statistic. The question naturally arises: which model better describes our data? To answer this, we'll compare the fit of the full model against the reduced model using a formal hypothesis test. Having established the least squares estimates for our reduced model, we now turn to estimating the error variance, denoted sigma squared, which quantifies the unexplained variability in our model. This estimate is derived from the residual sum of squares specific to the reduced model, divided by its corresponding degrees of freedom. With both the full and reduced models now fully specified, we face a fundamental question: which model is more appropriate for our data? To answer this rigorously, we employ a comparison F-test, a formal hypothesis test that allows us to determine whether the additional parameters in the full model provide a statistically significant improvement in fit. The test statistic is constructed using the difference in residual sum of squares between the two models. Specifically, we take the reduction in error sum of squares when moving from the reduced to the full model, that is, the reduced model's error sum of squares minus the full model's error sum of squares, and scale it by the difference in degrees of freedom between the two error terms. This scaled difference is then compared against the error variance estimate from the full model. The degrees of freedom for the numerator equals the difference in model complexities, while the denominator uses the error degrees of freedom from the full model. This ratio follows an F distribution under the null hypothesis that the reduced model is adequate. Having established how to estimate variance for the reduced model, we now confront a fundamental question: which model actually fits our data better? To answer this, we employ a comparison F-test, a formal hypothesis testing procedure that directly compares the explanatory power of two nested models. The test statistic is constructed as follows. We take the difference in sum of squared errors between the reduced and full models, that is, the additional unexplained variation when we remove parameters, and scale it by the degrees of freedom lost. This forms our numerator. The denominator uses the sum of squared errors from the full model, scaled by its own degrees of freedom, which provides an unbiased estimate of the error variance under the full model. The degrees of freedom in the numerator, denoted R, represents precisely how many parameters we've removed when moving from the full to the reduced specification. The denominator degrees of freedom corresponds to the error degrees of freedom available in the full model. This ratio follows an F distribution under the null hypothesis. A large test statistic indicates that the reduced model sacrifices substantial explanatory power, suggesting the removed parameters were indeed important. Conversely, a small statistic suggests the simpler model is adequate. We'll see on the next slide how this framework specifically tests whether treatment effects are equal across groups. Having established the mechanics of the comparison F-test in the previous slide, we now turn to the critical question of model selection. The test we construct here specifically evaluates whether treatment effects are equal across groups. This is our primary research question, and it directly determines what we place in the numerator of our test statistic. The numerator captures the reduction in sum of squared errors when we move from the reduced model, which imposes the equality constraint, to the full model, which allows treatment effects to vary. We scale this reduction by the degrees of freedom difference between the two models to obtain our mean squared difference. This ratio, compared against the mean squared error from the full model, tells us whether the observed improvement in fit is statistically significant or merely due to random variation. The choice of which model to compare is therefore not arbitrary. It flows directly from our substantive hypothesis about treatment effects. We are asking whether the data provide sufficient evidence to reject the simpler model in favor of the more complex one. This decision framework ensures our statistical test aligns with our scientific question. Now let's address the covariate itself. The covariate serves as a nuisance variable in our analysis. It's something we must account for statistically, but it's not the focus of our investigation. Our primary interest remains the treatment effects. The covariate is included in the model solely to reduce unexplained variation and prevent it from confounding our treatment comparisons. Because the covariate is merely a control variable and not a parameter of substantive interest, we do not conduct a significance test on it. Testing the covariate would be inappropriate and potentially misleading, as we're not making scientific claims about its relationship to the response. Instead, we simply allow it to adjust our estimates and reduce error variance. This distinction is important. We include the covariate to improve our inference about treatments, but we remain silent about the covariate's own statistical significance. In the next slide, we'll see how this principle translates into the structure of the analysis of covariance table, where you'll notice the covariate term appears but without an associated F-ratio for hypothesis testing. Now let's examine the analysis of covariance table, which organizes our statistical decomposition in a structured format. The table partitions the total sum of squares into three components. First, we have the treatment effect adjusted for the covariate, denoted as treatment given the covariate. This captures the variation in our response variable attributable to the treatment groups after accounting for the covariate's influence. Second, we have the covariate effect adjusted for treatment, which quantifies how much variation the covariate explains beyond what the treatment explains. Third, the error term represents unexplained variation. Each source of variation has associated degrees of freedom. The treatment has a -1 degrees of freedom, the covariate has 1 degree of freedom, and the error has n minus a -1 degrees of freedom, where n is our total sample size and a is the number of treatment groups. We calculate mean squares by dividing each sum of squares by its degrees of freedom. The F-ratio for testing treatment significance is the mean square for treatment divided by the mean square error. This ratio tells us whether treatment differences are statistically significant after adjusting for the covariate. Notice that we do not compute an F-ratio for the covariate, consistent with our earlier discussion that the covariate is merely a nuisance variable requiring adjustment, not a parameter of inferential interest. Before we proceed with our analysis, we need to verify a critical assumption underlying ANCOVA: the homogeneity of regression slopes. This assumption requires that the relationship between our covariate and the response variable remains constant across all treatment groups. To test whether the slopes are equal, we examine the interaction term between the covariate and the treatment factor. Think of this interaction as capturing whether the covariate's effect changes depending on which treatment group an observation belongs to. If this interaction term achieves statistical significance in our model, we have evidence of unequal slopes across groups. This would violate our assumption and suggest that the treatment effect depends on the covariate level in different ways for different groups. When slopes are unequal, the standard ANCOVA approach becomes problematic because we cannot simply adjust for a single covariate effect. Instead, we would need to consider separate regression lines for each treatment group or employ alternative analytical strategies. This diagnostic check is essential before interpreting our adjusted treatment effects, ensuring that our ANCOVA model is appropriately specified for the data at hand. Now let's return to our balloon example to illustrate these concepts in practice. Recall that we conducted an experiment examining the effect of 4 different colors on balloon inflation time. When we plotted the standardized residuals against the run order, we observed a clear linear trend. This trend is particularly important because it signals a violation of a fundamental assumption in our analysis: the independence of error terms. In other words, the residuals were not randomly distributed but instead exhibited a systematic pattern related to when each observation was collected. This dependent structure can bias our inferences if left unaddressed. However, we can remedy this problem by incorporating run order as a covariate into our model. By doing so, we account for the temporal or sequential effects that were driving the trend in our residuals. This adjustment allows us to isolate the true effect of balloon color while controlling for the systematic variation introduced by the order in which the experiment was conducted. This practical application demonstrates how diagnostic checking and model refinement work together to produce more reliable statistical conclusions. We now turn to the practical implementation of our solution. Having identified the temporal dependence in the residuals through our graphical diagnostic, we proceed to reformulate the statistical model by incorporating run order as a covariate. This adjustment allows us to explicitly account for the systematic variation that accumulates across the experimental sequence. By including this temporal component in our regression framework, we effectively partition the total variability into three distinct sources: the effect attributable to balloon color, the effect attributable to the sequential ordering of observations, and the remaining random error. This decomposition is crucial because it isolates the color effect from confounding temporal influences, thereby yielding more precise and unbiased parameter estimates. The resulting model provides a clearer picture of how color genuinely affects inflation time, independent of any drift or systematic change that occurred during the experimental runs. This approach exemplifies a fundamental principle in experimental design. When diagnostic analysis reveals violations of model assumptions, we must revise our specification rather than ignore the evidence. The data we are about to examine represents the complete factorial design with all 32 observations recorded in their original temporal sequence. We now turn to our experimental data, which consists of 32 observations organized by experimental order and color category. Each observation includes a measured response time in seconds. The data spans 4 distinct color conditions, with multiple replications across the experimental sequence. Before we proceed to formal statistical testing, it's important to recognize that this dataset exhibits considerable variability in response times, ranging from approximately 14 to 29 seconds. This variation motivates our next step: a rigorous analysis of variance to determine whether color category systematically influences response time, and whether the experimental order introduces confounding effects. The structure of this experiment allows us to partition the total variance into meaningful components. We can isolate the effect attributable to color, the effect attributable to order, any potential interaction between these factors, and the residual error. This decomposition is precisely what the analysis of variance framework provides, and it will enable us to test specific hypotheses about which factors genuinely affect our measured outcomes. As we move forward to examine the ANOVA results, keep in mind that we're seeking evidence of systematic differences among the color conditions while simultaneously accounting for potential ordering effects. Examining the analysis of variance table before us, we must focus on the interaction term between color and order. Notice that the interaction p-value is 0.329, which far exceeds our conventional significance threshold of 0.05. This tells us that the interaction effect is not statistically significant. What does this mean conceptually? The interaction tests whether the relationship between order and time depends on which color we're examining. A non-significant interaction indicates that the slopes, that is, the rate of change in time across the order sequence, are essentially the same across all 4 color groups. In other words, color and order do not interact meaningfully in their effects on the response variable. This is an important finding because it simplifies our interpretation. We can confidently state that the effect of order on time is consistent regardless of color category. The color groups may differ in their average times, as suggested by the significant color main effect with p equals 0.041, but they follow parallel trends across the order variable. Therefore, we conclude that the slopes are homogeneous across color groups. This parallel relationship validates the assumption of equal slopes when modeling these factors together. Examining this revised analysis of variance table, we observe a substantial shift in our conclusions compared to the previous model. Notice that the color effect now yields an f-statistic of 6.23 with a p-value of 0.002, which is highly statistically significant. This represents a marked improvement over the previous result. The critical change here is that we've removed the color by order interaction term from the model. By doing so, we've eliminated 3 degrees of freedom from the error term, reducing it from 24 to 27. This reduction in error degrees of freedom actually increases our error mean square slightly, from 6.598 to 6.749. However, the adjusted sum of squares for color has increased substantially to 126.134, which more than compensates for this change. The practical interpretation is clear. When we assume that the color effect is consistent across all order conditions, that is, when we assume no interaction is present, we gain statistical power to detect the color effect. The data now provides strong evidence that different colors produce significantly different response times. This demonstrates an important principle in experimental design. Removing non-significant interaction terms can strengthen our ability to detect main effects, provided our assumption of no interaction is reasonable. Let me walk you through the interpretation of this ANOVA table for the time response variable. We're examining the effects of color and order on our outcome measure using adjusted sums of squares, which accounts for the sequential nature of our factor entry. Looking at the color factor, we have 3 degrees of freedom and an adjusted sum of squares of approximately 126.134. The corresponding mean square is 42.045, which yields an F statistic of 6.23. Most importantly, the p-value is 0.002, which is well below our significance level of alpha equals 0.05. This tells us that color has a statistically significant effect on time. We can reject the null hypothesis that all color treatment means are equal. Notice that the order factor shows a sequential sum of squares of 123.424, but we don't have the corresponding F statistic and p-value displayed here. The error term has 27 degrees of freedom with a mean square of 6.749, which serves as our denominator for hypothesis testing. The total sum of squares across all 32 observations is 431.799. So our next step is to determine which specific color treatments differ significantly from one another. We have established that significant differences exist among our treatment groups at the conventional significance level of 0.05. However, rejecting the null hypothesis of equal treatment effects is merely the first step in our analysis. The critical question now becomes, which specific treatments actually differ from one another, and which treatment effects are meaningfully different from zero? To address this question, we employ the method of contrasts. Contrasts allow us to construct targeted comparisons between treatments or groups of treatments, moving beyond the omnibus test to identify the precise nature of the differences we have detected. Within the analysis of covariance framework, we retain the ability to construct confidence intervals for these contrasts using the least squares estimates derived from our full model. These estimates incorporate the covariate adjustment, providing us with precise point estimates and interval estimates for the specific comparisons of interest. This approach maintains the efficiency gains from our covariance adjustment while allowing us to make detailed inferences about which treatment combinations differ substantively. Having established that significant treatment differences exist at the 0.05 significance level, we must now identify which specific treatments actually differ from one another. This is where contrasts become essential. In the context of ANCOVA, contrasts allow us to construct targeted comparisons between treatment groups while accounting for the covariate structure. The key advantage here is that we can leverage the least squares estimates derived from our full model to create confidence intervals for these contrasts. This approach maintains the efficiency gains we obtained from including the covariate in our analysis. Rather than relying on simple pairwise comparisons, contrasts give us the flexibility to test meaningful hypotheses about combinations of treatment effects. In the next section, we will examine how to calculate the variance of a contrast, which is fundamental to constructing these confidence intervals and conducting hypothesis tests about specific treatment comparisons. Now that we've established which treatment effects warrant investigation through our contrast framework, we must turn our attention to quantifying the precision of these estimates. The variance of a contrast is fundamental to constructing confidence intervals and conducting hypothesis tests. Recall that when we work with the ANCOVA model, the variance of any linear combination of our least squares estimates depends critically on the covariance structure of those estimates. Specifically, the variance of a contrast is proportional to the sum of squared coefficients, weighted by the underlying error variance and adjusted for the design matrix. This relationship allows us to move beyond point estimates to interval estimates that capture our uncertainty. The calculation becomes particularly important in ANCOVA because we must account for the covariate adjustment in our variance computation. Once we have established the variance structure for our contrasts, we are positioned to construct confidence intervals and perform multiple comparison procedures, which we will address in the subsequent section. These intervals provide the inferential framework necessary to make rigorous statistical conclusions about which treatment differences are genuinely non-zero. Having established the variance structure for our contrasts in the previous section, we now turn to the practical task of constructing confidence intervals around these estimated contrasts. This represents a natural extension of the estimation framework we've already developed. The key insight is that we can leverage the variance formulas we derive to build intervals that quantify our uncertainty about the true contrast values. These intervals will provide us with a range of plausible values for each comparison of interest, accounting for sampling variability. As we move forward, you'll notice that we're building directly on the foundational concepts from our earlier work on variance estimation. The confidence intervals we construct here will serve as the basis for our hypothesis testing procedures, which we'll address in subsequent slides. This methodical progression from estimation to inference is fundamental to comparative analysis in experimental design. By establishing these intervals first, we create a solid statistical foundation before we engage in formal hypothesis testing. Having established confidence intervals for our contrasts in the previous section, we now turn to hypothesis testing to determine which pairwise comparisons among our group means are statistically significant. The Tukey correction, also known as the Tukey honest significant difference test, provides us with a rigorous framework for conducting multiple comparisons while controlling the family-wise error rate. This is crucial because when we perform many tests simultaneously, the probability of committing at least one type 1 error increases substantially without proper adjustment. The Tukey method adjusts our p-values accordingly, ensuring that our significance level remains valid across all comparisons. Looking at our results, we examine the difference of means between each pair of color groups, along with the standard error of that difference, the resulting t-value, and most importantly, the adjusted p-value. By comparing these adjusted p-values to our chosen significance level, typically 0.05, we can identify which specific pairs of means differ significantly from one another. This systematic approach allows us to move beyond simply knowing that group differences exist to pinpointing exactly which groups differ meaningfully. Now let's examine the results of our Tukey simultaneous tests for the balloon experiment. We're comparing all pairwise combinations of the 4 color groups to determine which means differ significantly from one another. The table presents 6 comparisons, each showing the difference in mean time between 2 color groups, along with the standard error, the test statistic, and the adjusted p-value. The Tukey correction accounts for multiple comparisons, controlling our overall type 1 error rate. Looking at the adjusted p-values, we need to identify which pairs fall below our significance threshold of 0.05. Comparing colors 2 and 1 yields a p-value of 0.0209, which is significant. Colors 3 and 1 show a p-value of 0.0358, also significant. The comparison of colors 4 and 2 gives us 0.0169, significant as well. Finally, colors 4 and 3 produce a p-value of 0.0289, again significant. The remaining comparisons, colors 4 and 1, and colors 3 and 2, both have p-values well above 0.05, indicating no significant difference. This pattern suggests that certain color groups produce meaningfully different inflation times, while others perform similarly. We'll synthesize these findings on the next slide to draw our final conclusions about the balloon experiment. Now let's interpret these results from our Tukey simultaneous test. The key decision rule is straightforward. We reject the null hypothesis of equal means for any pair where the adjusted p-value falls below our significance level of 0.05. Looking at our pairwise comparisons, we have 4 pairs that meet this criterion. Color 2 versus color 1 shows a p-value of 0.0209. Color 3 versus color 1 yields 0.0358. Color 4 versus color 2 gives us 0.0169. And finally, color 4 versus color 3 produces 0.0289. These 4 pairs represent statistically significant differences in mean response time across our color groups. Conversely, The comparisons with p-values exceeding 0.05, such as color 4 versus color 1 and color 3 versus color 2, do not provide sufficient evidence of true differences. The Tukey procedure controls the family-wise error rate, meaning our confidence in these conclusions applies simultaneously across all pairwise comparisons. This is a crucial advantage over conducting multiple independent t-tests, which would inflate our overall type 1 error probability. With these conclusions established, let's now examine how we would implement this analysis in SAS. Now that we've established our conclusions regarding pairwise comparisons, let's examine how to implement these analyses in SAS using the balloon example dataset. We'll work through the PROC-GLM procedure, which is the General Linear Models procedure in SAS and is essential for conducting analysis of variance and regression analyses. The code demonstrates two complementary approaches. First, we specify our model with inflation time as the response variable and color along with the continuous predictor X and their interaction as explanatory variables. The class statement identifies color as a categorical variable. We then request Tukey's honestly significant difference test at the 0.05 significance level to conduct all pairwise comparisons among color groups. Additionally, we use the estimate statement to obtain the regression coefficient for X, and the output statement creates a new dataset containing predicted values and residuals for subsequent diagnostic checking. This comprehensive approach allows us to simultaneously evaluate group differences and the relationship between our continuous predictor and the response. Continuing with our balloon example, we now implement the analysis in SAS using PROC-GLM. The first approach specifies a model with color and the continuous predictor, along with their interaction term. This allows us to test whether the relationship between the continuous variable and inflation time differs across color groups. The second approach provides more detailed output. We declare color as a categorical variable using the class statement, then model inflation time as a function of color and the continuous predictor. The means statement with the Tukey adjustment gives us pairwise comparisons among color groups at the 0.05 significance level. The estimate statement allows us to extract and test the slope parameter for the continuous variable. Finally, the output statement saves predicted values and residuals to a new dataset, which we can use for diagnostic checking. This comprehensive specification demonstrates how to simultaneously evaluate group differences, quantify the relationship with a continuous variable, and generate residuals for model validation. These tools form the foundation for our next topic, where we extend this framework to account for blocking structures in experimental designs. We've now completed our examination of the general linear model procedure and its application to analyzing the relationship between a continuous response variable and categorical predictors. The code you see here demonstrates how to specify class variables, construct model statements with interaction terms, perform post-hoc comparisons using Tukey's method, estimate specific linear combinations of parameters, and generate predicted values and residuals for diagnostic assessment. Moving forward, we'll shift our focus to a more sophisticated experimental design framework. In our next session, we'll explore randomized complete block designs, which represent a fundamental advancement in controlling for nuisance variation in experimental settings. These designs introduce blocking as a systematic method to account for known sources of heterogeneity that might otherwise inflate our error variance and reduce statistical power. We'll examine how blocking structures are incorporated into our analytical models, how to properly specify these designs in SAS, and most importantly, how blocking affects both our inference and our interpretation of treatment effects. This represents a critical step in your development as a statistician, as blocking is one of the most powerful tools available for improving experimental precision.